All right, nerds, so today for the exciting conclusion of Unit 1.3. On Friday, the last thing that we talked about was this difference quotient thing, and I know it went really fast, but I'm not testing you on it right now. The difference quotient is just a fancy way of saying the average rate of change between any point and its y value, and then a little bit further to the right on the x-axis. That's all that says. You don't really have to know that right now. What I do need you to be good with, and because I think you're probably not perfect with it yet, after I get through the lesson, I'll do another example of it, is this whole setup here where we took a table of data, we found average rates of change, we then found the change in those average rates of change, and we said that this number represents the slope of our rate of change function, if you recall doing that. We said that we had a rate of change of 0, instantaneous rate of change in IROC, an instantaneous rate of change of 0 at x equals 3. We used this slope of 2 and that instantaneous rate of change of 0 at x equals 3 to write the equation of a linear slope function. And because I know I need you to have that skill, and I know that it's probably not cemented in your brains yet, after the lesson, I'll make up an example of one of those, and you could choose to squeeze it wherever you'd like to, or just watch it, completely up to you, okay? Surprise, we're still talking about more rates of change, straight lines and quadratics. Essential thoughts. A graph is said to be increasing if the y values go up as the x values go up. So that means as you go from left to right, you're going up, increasing. A graph is said to be decreasing if the y values go down as x goes up. That means from left to right. So as x goes up, y goes down. And that's all these words say. Now the essential thoughts of concavity. This whole structure is concave up, but that has nothing to do with increasing, decreasing. It has everything to do with the rate of increasing, decreasing. A graph is concave up when your rate of change or average rate of change is increasing. So here, my graph is decreasing, but it is concave up. So that means my graph is decreasing, but since it's concave up and the rate of change is increasing, I could say my graph is decreasing at an increasing rate. My graph is increasing at an increasing rate. So if you say concave up, that means rate of change is increasing. So decreasing at an increasing rate, increasing at an increasing rate. And that's true for rate of change and average rate of change. Concave down, same logic. Concave down is where your rate of change is decreasing or your average rate of change is decreasing. But decreasing rate has nothing to do with your y values increasing or decreasing. This side of this curve is increasing. This side of this curve is decreasing. This side of the curve then is increasing at a decreasing rate. And this side is decreasing at a decreasing rate. And these things kind of play games with the English language, to be honest with you, especially this one right here, decreasing at a decreasing rate. So let's say you've got the numbers. Let's say I give you a bunch of xy's and you calculate your average rates of change. So you have found your rates of change. And your rates of change do this. -5, -10, -16, -23. I said 23, I wrote 7, ... Okay? I think we can all agree that because these rates, remember, these would be rates of change. If these are rates of change, not y values. I think we can all agree that all these rates of change are negative. That means my graph is decreasing. Now look at the change in the rate of change. -5, -6, -7, then clearly -8, -9, so on and so forth. This, because my rate of change is negative, is decreasing. And because it's decreasing and getting worse and worse decreased, or more and more negative, like how do you say that? You say that the rate of change is, yes, it's growing in magnitude, 5, 6, 7, 8, 9, but this is technically decreasing at a decreasing rate because these values themselves are going down also. -7 is smaller than -6. -6 is smaller than -5. So when you say decreasing at a decreasing rate, that makes you want to think, I know, it makes you want to think this. Going down but slower and slower. But no. This is decreasing at an increasing rate. This is decreasing at a decreasing rate. And that is an issue for the English language. Because you want to think, yeah, but isn't it getting more and more negative? So isn't that negativity increasing? You go, yeah, English. Okay? Essentially, if the rate of change is increasing, you know it's concave up, and every time you describe something like that, you say that rate of change is increasing. Decreasing at an increasing rate. Increasing at an increasing rate. If it's concave down, anytime you describe the change of rate of change, you have to say decreasing. Increasing at a decreasing rate. Decreasing at a decreasing rate. Okay? All right. Here we have a very, very basic quadratic, x squared minus 1. What we're going to do is we're going to fill out the y table here, the xy table. So just plug in the number in, squaring it, subtracting 1. So squaring 4 minus 1. This number squaring 1 minus 1. Squaring 0 minus 1. Squaring 1 minus 1. Squaring 4 minus 1. Squaring 9 minus 1. All right, that was easy peasy. Because the change in x is always 1, I can calculate my average rate of change because these are equal length intervals. They're all an interval of length 1, yes? And because I'm going up by 1 on the x-axis, when I go to find this average rate of change, you know, because it's y2 minus y1 over x2 minus x1, every one of these x2 minus x1s gives us positive 1 every single time. So our average rate of change is essentially just the difference of the y's, because the difference in the x's is always plus 1. So let's get our average rate of change. 0 minus 3 over 1. -1 minus 0 over 1. 0 minus -1 over 1.
What do you mean over 1? What were you doing?
The
average rate of change.
if every one of these differences between x and the x before it is 1.
Oh, okay.
Because we just went by 1s on the table.
Okay.
Now I was only able to get away with that because this counted by 1s. If it had counted by 2s or 3s or 5s, I would have had to actually have a fraction, but because it's counted by 1s, we just go, oh, over 1.
Okay.
3 minus 0 over 1, and 8 minus 3 over 1. Here are our average rates of change. So let's say you didn't know any of this, and all you knew was this. What can you tell? Well, if you weren't told it was a quadratic, could you figure out if it's a quadratic? Yes, you can. It's kind of letting the cat out of the bag, but if you go from here to here, do you notice that it's just plus 2? And then from here to here is plus 2, plus 2, plus 2. We instantly know it's a quadratic. Not because these are 2's. We know it's a quadratic because they're all the same number. Anytime, if the average rate of change was all the same number, then we know we're dealing with a straight line. But if the change in the average rate of change is the same number, then we know we're dealing with a quadratic. This is future knowledge, but if I had to go to the third change to see the same number, it'd be a cubic. If I had to go to the fourth change to see the same number, it'd be a fourth degree polynomial. So basically, when the change becomes one number, you have found the degree of the polynomial. That's section 1.4. That'll be for after the quiz. So, but right now, no knowledge, we know we have a quadratic. Oh, we have a quadratic. You know what all quadratics have? They all have a vertex. They all have a vertex. And without seeing the equation, we could see where that vertex is. But how? These are rates of change. All these rates of change are negative, where my graph is decreasing. These rates of change are positive, where my graph is increasing. And anytime a graph changes from increasing, decreasing, or vice versa, you have found a turning point. Quadratics only have one turning point. So just looking at this, you can see at which x value we changed from decreasing to increasing. I'm hoping you could see that it happened in this zone, right here, between these two intervals. It happened here. And you know what's between those two intervals? The number x equals 0. Because this interval ended with a 0, this interval began with a 0. So we know we have a quadratic. We know its turning point happens at x equals 0. And by coincidence, it happened at x equals 0 because what is the rate of change at all turning points? 0. So it's coincidental that the rate of change would have been 0 here at x equals 0. That's a coincidence. It didn't have to happen at x equals 0, it just did. Okay. So it says, what do you notice about the average rate of change over consecutive equal length intervals? We notice that the average rate of change is doing what? What's the behavior of this average rate of change? It's increasing. What does that tell you about your quadratic? It's concave up. Okay, well, if the quadratic is concave up, it looks like this. It means it's an upwards facing quadratic. So even without an equation or a table of x, y values, we could see what the x value of our turning point is, which means we know what the rate of change is at that x value. We wouldn't know what the y value of that turning point is. We don't know that without the stuff that's under my hand. But you know where it happens. You know it's a quadratic because it took the rate of change of the average rate of change to get to a solid number. And because these numbers are going up, we know it's concave up because our average rate of change is increasing. Yes?
So an example of the average rate of change decreasing numerically would be those twos would be minus, or am I wrong?
If the average rate of change, if the change, because this is the change in here, let's do it like this. This is delta AROC. Delta stands for change. If the change in the average rate of change is positive, then it's concave up. If the change in the average rate of change is negative, then it's concave down. So yeah, if every one of these numbers was a negative number, then we know we're concave down. Or without even finding those, we could see that these numbers were quote unquote falling. You see these are rising. But yeah, so if these were positive, guaranteed to be concave up. If these are negative, guaranteed to be concave down. And the fact that they're all the same number told me it was a quadratic. Not that it's a 2, that's coincidental. Tell you what this does tell me though. If I wanted to write the equation of the rate function, which is the thing I'm going to show you after the lesson, to show you again I should say, the slope of that rate function is 2. I know that. That's the slope of that rate function because of those numbers all being 2's. But I'll give you an example after the lesson of that happening. Here we have a quadratic. It says find the average rate of change from -1 to 3. So let's grab the coordinates. X equals -1 gets me this coordinate right here. -1 comma -4. And 3 is here, so 3 comma 4. Four minus -4 over 3 minus -1. That is, something's wrong. No, it's not. I can count. For some reason, in my mind, this was 5. It's like something's way wrong. Okay, this is 8 over 4. So I have an average rate of change between those two dots of 2. Not bad, right? Average rate of change, everybody should be really good at that by now. Okay. So let's find the equation of the secant line that contains those points. This is just saying what the y value is when x was -1. We got it was -4. This just says what the y value was when x was 3. We got it was 4. So we're now going to write the equation of the line that has that slope and goes through those 2 points. It's called a secant line because it goes through the parabola twice. We already know the slope of this secant line is 2. And now we can grab either one of our x comma y's, doesn't matter which one you choose, drop it in for x and y, and solve. I don't want to deal with the negatives. If you're cool with that, I'm just going to use those 2 numbers up there. Gonna write in orange and green. Don't tell my wife, she'll be mad at me. Because boo Miami. Getting b by itself gets us -2. Our secant line is y equals 2x minus 2. And then it says to sketch the graph. Yes?
Where did you get 4 and 30 from?
Right there. I just took one of the 2 known coordinates, and I could have used -1, -4 if I wanted to. I just didn't want to have to mess with the negatives. And then it says to sketch the secant line. Let's see. I know it goes through -2, so I got to get through those 3 blue dots to the best of my ability. Hey, good enough. Good enough. Oh, and it does actually hit right there. That was cool. Good guess. Bless you. Goodness. So how are we feeling about those examples so far?
Good.
Good. Feeling good. Okay. Number 8. Example number 8, I should say. Oh my goodness. I just realized that I have 2 different programs recording me right now. Did I never hit start recording? I am recording the wrong thing. I didn't hit start recording on OBS. That means there is no audio on this video. That really sucks. I'll figure it out. I'll figure out a way to splice them together before I go home. We'll figure it out. All right, number 8. Average rate of change of h of x over this interval from 0 to 4 is 18. We need to use that knowledge to find this missing value. Can we agree that this is a y value? Because it says h of x. This is an unknown y value. And we're going to solve for it. All we know is that the average rate of change between x equals 0 and x equals 4 is 18. But the average rate of change is just finding slope. So y2, and actually this will be y2. y2 minus y1, which is y equals 2, over x2, which is 4, minus x1, which is 0. That's all we're being asked to do. But we know that equals 18. So y2 minus 2 over 4 is 18. Alrighty, well, I know you don't like fractions, so how are you going to get rid of it? Multiply by 4 on both sides. That gives you y2 minus 2 equals 36 times 2, 72. Add 2 to both sides, and we found out that that missing y value is the number 74. There it is. Questions I got in period 7. Why is it the inequality? It's just showing you that the graph exists between all of these x's. That's it. Why do we have these other numbers then? Oh, just to mess with you. You actually don't need any of those if you're finding average rate of change. They're not necessary. Yes, sir?
What number is outside the parentheses? Is that 4?
That's the 4. That's me getting rid of the divide by 4.
Okay.
That's me canceling this right here.
So then it would be y2 minus 2 is equal to 8. Oh, okay.
18 times 4. 72.
Oh, okay, not.
You have to distribute it to both sides.
Yeah, I just didn't see like the step that you took after that.
Okay. Questions on that one? Finding a mystery value? No? All right. Suppose the demand for a product can be expressed as this thing, where x is given in units of 1,000. Just find the average rate of change. I'm so sick of average rate of change. Find the average rate of change of demand, because this is the demand for an object. Find the average rate of change of demand when the items demanded increase from 2,000 to 4,000. We are not going to use x equals 2,000 and x equals 4,000. We're going to use x equals 2 and x equals 4, because it says x is 1,000 units of 1,000. We're literally just going to plug those two x values in and get a y value. I'm going to use a calculator for that and make my life easy. .2 times 2 squared. So anytime I substitute, I use parentheses. Substituting x equals 2 gives me 8.5. And because I don't want to have to retype all of that, because I know my equation's staying the same, I'm just going to replace those 2's with 4's. I pressed up twice, hit enter, and then I can just go highlight, replace this 2 with a 4, and replace this 2 with a 4, and then hit enter. Poop. There it is, 13.2. Now we just find the average rate of change between those two values. Quick maths, 4.7 over 2, 2.35. And that's, 1,000 units. Okay. So what is that telling us? It didn't ask us, but what is that telling us? It tells us that as we increase from 2,000 to 4,000 units, the demand is still rising. The demand is rising at 2.35 thousand units. Now let's find a different average rate of change and see what happens. This time I'm going from 1,000 to 5,000. And again, I don't feel like typing all that in. So I'm just going to go up, and where there was a 4, I'm going to type a 1. Hit enter. 6.75. And do it again. And where there's a 1, I replace it with a 5. $16.15. All right, 16.15 minus 6.75 is 9.4 over 4. Hey, how about that? 2.35 again. That's really interesting. But not surprising. And here's why. Let me take my little, actually, that nerd's paper won't work. I got an idea. I'm going to take this Tupperware. I had my yummy grapes in it today. Interesting. Two completely different x values, exact same average rate of change. Well, check this out. The edge of this Tupperware is a straight line-ish, represents the slope of that secant line. That, remember, slope of secant line is an average rate of change. Now, I could take that line and go up and find two more x's that has the exact same rate of change. I could go down and find two that have exactly the same rate of change. So no, it's not surprising. It's neat that we found another one that's got the exact same rate of change, average rate of change. But you know what's even cooler than that? So yeah, I can find an infinite number of xy's that'll give me that 2.35, right? Which I know isn't this. This had a slope of 2. But check this out. Not only can I find a secant line, meaning goes through 2 points, I could find a tangent line, which would be the place where the curve has an instantaneous rate of change, equivalent to this average rate of change. And this is a very fundamental idea in calculus, that if the average rate of change exists between two x's, that exact same number is an instantaneous rate of change between those two x's somewhere. It's not at the average point, but it happens somewhere between them. It's fundamental to calculus. So that's why we saw something like that, so that you could see that that happens. And then we flip it over. And we're going to talk about Nikola's technology. The graph below gives Nikola Technologies revenue, capital RFP, for Bluetooth headphones. The x-axis represents the price of the headphones. We're going to label this price in dollars. And that's price that we're charging. Price in dollars. And the y-axis is revenue in millions. So revenue, and this is in millions. And then it says to label the curve y equals capital RFP. All right. You guys know what revenue is? It's money that's coming in. It's not necessarily profits. It's just money that's coming in. Okay? And we can't deal with profits because we don't know how much these things cost to make. That's a completely different kind of question. But here we have how much money comes in based on how much we're charging for our headphones. It says, at what prices will the tech company make no money? So where does revenue equal 0? Where do we see that happening?
$55.
Revenue?
0.
What you identified the maximum revenue.
Oh.
This one's revenue is 0, and the revenue is 0 happens here at 0 and here at 110.
So we stop making money out of $110.
Well, it says why. Okay, how about this one? Why is revenue 0 when we're charging 0?
You're not making any money.
Yeah, clearly we're giving these things away for free. So we're saying free headphones. But why do we stop having money come in at $110 max?
People don't buy it because it's
Too expensive. There you go. Yep. Turns out people just won't buy them for $110. Might as well be $1,000 at that price. We're not buying them. Okay. Now, two employees are having an argument. Employee 1 says $45 would be the best selling price for their company. We got to put these things at $45. That's the best thing for our company. Employee number 2 says, I really think they should be more than $50. The question says, is either of them on the right path?
Yes.
I would say yes. And here's why. Employee number 1 says $45. And employee number 2 looks at the graph and goes, it should be more than 50. And I would say that employee number 2 is onto something, because you'll notice the maximum revenue happens to the right of $50 per set. So if the goal of our company is to maximize revenue, what would be the best price to charge for these things? $55. Here is maximum revenue. And how do we know? Well, we could say because it's the maximum of the curve. Or we could get really technical, and we could say because $55 is where our graph stops increasing and starts decreasing. It's where we stop increasing and begin decreasing. Part D. Between a price of 0 and a price of 55, so from here to here, how does revenue change on average when the price of the headphones increases by $1? Literally, what is the average rate of change? Y2? Well, we're going to have to guess Y2. Where do you want to say that is about?
400.
400. You know this is 2000, right?
You said Y2, so I want to.
Yeah, Y2.
From the bottom.
No. Like I said, these 2 points. Anyway, I'm gonna say about 2050. It feels about 2050 or 2075-ish, somewhere around there. It doesn't look like it quite hit 2100. So 2050 minus Y1, which would have been right here at 0, over 55 divided by 0. Whatever the number 2050 divided by 55 is. About 37.27. You realize that this is change in revenue in millions.
I'm so lost. You told 2050 thing. What did you? It's because it's the Y. He's talking about the Y. Yeah, what is the Y? Oh, God.
That's the maximum Y value, dude.
Equals 55. What is the Y?
At x equals 55, we're above 2000.
It's like slightly above it. Oh, I understood.
Okay. So we're saying that's happening at 55, 2050. That's what we're estimating that. So,
You just guessed it was 2050?
well, I mean, it's not quite to 2100.
Yeah.
You can see it didn't make it halfway, so we just called it 2050 just to eyeball. Without an equation, we can't be exact. So yeah, we've got an average rate of change of an increase in average rate of change. No, I said it right the first time. The average rate of change is $37.27 million per every $1 increase in price. That's crazy. That's revenue. That's the change in revenue from free headphones to headphones that are $55. So here's what it's saying. So like if we only sold them for $1 a piece, we would make $37 million in revenue. If we sold them for $10 a piece, we'd make $370 in revenue. Okay, that's what we're saying. If we sell them for $100 a piece, well, we're not making that much, unfortunately, because the graph tells us so. But it maximizes at 55. And then the last question isn't even really math-based. It just says, are there any reasons or times when the price would adjust and why? And it's only worth talking about because it's real world. There's not even anything to write. It's not math. So are there times when we might adjust the price? Black Friday, yeah, sales around holidays. Why else might we adjust our price?
Coupons?
Coupons, yeah. What else?
If it was something new.
If it's something new. What if this is the newer technology and we have to discount outdated technology? So as a company, we can either discount our outdated technology or we could say, hey, this is the newest, better stuff. We could charge even more for it. So, of course, there are always going to be reasons why prices fluctuate, okay? Now, before I cut you loose, though, what I wanted to do was give you one of those examples where we want to try to find a rate function, okay? So I'm going to make up a function for you real quick, and you can have this written down somewhere, or you could just, watch and relearn because we did it yesterday. So bonus example, let's say I give you quadratic. So I just made up this quadratic. And let's say I give you a table of values. So I've just made up a quadratic. I'll save you the calculation time. These are the y values that you would get. Just like that. Why? There's always an interruption. Why? Anyway, so if I had asked you to find some average rates of change, let's find some average rates of change. From here to here, your average rate of change, well, because these are all going up by +1, all we have to do is find the difference in the y's. And -7 minus -27 is +20. 5 minus -7 is +12. 9 minus 5 is +4. And 5 minus 9 is -4. So average rates of change were positive until right here. And then they started being negative. Increasing, negative. What does that tell me? What's always going to happen when our rate of change changes from increasing to decreasing and vice versa? What happened? Not an inflection point. A turning point. We have a turning point at x equals 2. And that turning point is always going to be a place where rate of change is 0. That's true for all turning points. So right here, because I went from increasing to decreasing, there's a turning point at x equals 2. Now let's find the change in our average rate of change. From 20 to 12, minus 8. From 12 to 4, minus 8. From 4 to -4, minus 8. Because this only took me a second row of this whole finding differences thing, I know I'm dealing with a quadratic because it was row 2. More specifically, because the change in my average rate of change is negative, what does it tell me about my curve? No, it doesn't tell me the curve is decreasing. If the change in the average rate of change is negative, concave down. Here's what happened. My average rate of change was decreasing. That's why it's concave down. Or we could say because the rate of change of the average rate of change is negative. Both those things say concave down. So we have a downward facing parabola. And this number right here would be the slope of our rate of change function. And a coordinate that is going to be x comma rate of change is needed to help us find the equation here. We have one of those coordinates. At x equals 2, the rate of change is 0. And now we can write a y equals mx plus b that gives us the rate of change function for this quadratic. Let's see, plugging in 2 had better get me a 0. So negative 16 plus b is 0. I plugged in this xy. I did this. And that's how I got the b was positive 16. What this does for us is it will give us the instantaneous rate of change at any x value we want. So at x equals 1, you'd have an instantaneous rate of change of positive 8. There. So that was what I was talking about finding the rate of change function.